yeah, I've already pressed go. Right, here we go. So I'm going to look at reactions of benzene. I've said previously that these don't undergo electrophilic addition like we would have expected an alkene to do. So we're going to look at something different. Now, our benzene ring has our delocalized ring of electrons, and if you remember, this was where we had overlap of p orbitals, which each had an electron in, which then overlapped and delocalized, which gave us stability with our benzene. Okay, so it reacted slightly differently than we expected. It was a lot more stable in terms of the enthalpy of hydrogenation. It was in lower energy. It released less energy when we hydrogenated it. Yeah, ramble. But because these electrons are still relatively accessible, they're above and below the sort of plane of the molecule, these can get involved in reactions. But instead of electrophilic addition, what we see here is electrophilic substitution. Okay, so electrophilic, we've got an electrophile involved. It loves electrons. Okay, it's got to really love the electrons in our ring. Okay, that's the idea of electrophile. Substitution, it's going to swap something out. Okay, what are we going to swap out on this? Well, I don't know, what's not a lot going on in there. Our options are limited. So I'm going to do a general mechanism, and there are a few kind of tips, hints, kind of things that we do need to worry about in the course of all this. So I think we'll just start with a general one. So let's start with E. Okay, it's an electrophile. I've shown a positive charge on it because that's going to make it really love our electrons. So we need to put some curly arrows on to say where things are going to go. So remember, curly arrows show the movement of electrons. Where are my electrons? In the ring, you say. Okay, so my electrons are going to be coming from the ring. So drawing from there, going to the electrophile. So now we're going to form a new bond from the benzene ring to the electrophile. So it's not going to stick in the middle, okay, it's going to be attached to one of the carbons. So there's my E, it's attached there. Now, remember, attached to all the corners is a hydrogen, so there is a hydrogen attached onto this. That's not gone anywhere yet. This carbon now has formed 4 bonds. What's happened to the electron ring? Well, that's sort of been broken up now because 2 of the electrons have gone over to form this bond with the electrophile. So it's not intact. So I'm going to show it as a dotted line. You can show it as a solid line if you like, but I'm just sort of suggesting it's been broken up. I'm not showing my other hydrogens attached because they're not involved. It's still a skeletal formula. We only show the hydrogens when they're important to the reaction. Looking over here, there was no charge here. There's a positive charge on the electrophile. So that positive charge has got to have gone somewhere, and that positive charge now is kind of shared amongst the remaining electrons. Okay, I shouldn't really use the word sharing, but it's that delocalized ring is kind of capturing that positive charge. Now, what I don't want anybody to do is let's do this in pencil and with a line. So our positive charge is not too close to the reacting carbon here. Okay, we don't want it shown anywhere near there. So bury it well in the ring over here. Okay, well in the body of the molecule. As far away as you can get from there, just so no one can complain. Right, I'll just rub this out because it might make it look messy. So remember, don't show the positive charge too close to the carbon here. Now, another thing to be aware of while I'm on the topic of where people can lose marks, when we've broken our ring, don't let it encroach too close. You can't even see these on here probably. Don't let it encroach close to this carbon here. Make sure it doesn't go beyond carbon number 2 and carbon number 5. Okay, so so my broken delocalized ring, not past carbon 2 or carbon 5. Okay, so that's carbon 1 that I'm calling here. So 2 and 5. So keep it tidy there. Anyway, back to the mechanism. What's going to happen now? Well, benzene likes its ring. It wants to get its ring back. So our electrons in our carbon-hydrogen bond here are going to return to the ring. Okay, so from the bond to the ring. Then what we have down here is we've got our electrophile attached onto it. The hydrogen has got bored and wandered off over there, and our beautiful ring has been re-established. It's now delocalized all happily again. So that is electrophilic substitution. It's a nice easy mechanism in lots of ways. Key points where people go wrong. Showing the electrophile moving to here. Okay, it isn't, it's the electrons that are moving. The ring, once it's been broken, do not extend beyond carbons 2 and 5. Okay, so when we made this sort of horseshoey type shape here, don't let it encroach over towards this one. Likewise, the positive charge is not on this carbon here. It's somewhere delocalized, sort of stabilized around the ring. Arrows, that shouldn't be too bad, but just make sure it's going into the ring rather than to a carbon atom directly. Yeah, I'm going to write these out. Okay, so 1 arrow to the electrophile. 2, I'm going to call it a horseshoe, not past carbon 2 and carbon 5. Okay, so don't encroach over there. 3, the positive charge. It's in the ring, not on the carbon. And number 4, what did I say number 4 was? Okay, yeah, the HC bond breaking. The arrow to the ring. Okay, into the body of the thing, not carbon. Not to carbon. Okay, well, I'm going to have a pause and a cup of coffee, and then she'll be back and we'll do another one in a moment. Right, okay, nitration. Now this is an important reaction. It's a really, really useful one. I'm going to start off by showing you how we make the reacting species. Yeah, so let's just crack on. So what we have is H2SO4. Okay, so sulfuric acid. Now this is going to be a catalyst in this, so remind me to tell you about where it reforms at the end. Now we want to make ultimately an electrophile. Okay, this thing here. This is a nitronium ion. Sometimes see it called a nitrile cation, I think, but I always call it a nitronium ion. So we've got to have a nitrogen containing species in order to make this nitronium ion here. So the nitrogen containing species that we're going to use is HNO3, nitric acid. So I've got sulfuric acid reacting with nitric acid. Acid reacting with a nitric acid? What? What witchcraft is this? An acid reacting with an acid? Yeah. Yeah, so this sulfuric acid is actually a stronger acid than the nitric acid. So what we form over here is HSO4 minus. So it's lost a proton. It's being acidic. Its proton has disappeared all the way over here. To my nitric acid, which is now protonated. So yeah, I suppose you could call this acting like a Bronsted-Lowry base if you've done that. It's accepted a proton. It's donated its lone pair. Okay, so now this species here is the one that's going to get involved over here, HNO3 plus, and what happens is it essentially falls apart, okay, and it just releases H2O. Key things to remember on this is concentrated, this is concentrated, so if you're asked for two reagents you need concentrated sulfuric acid and concentrated nitric acid in order to form our nitronium ion. You do need to know these two equations to show the formation of the electrophile, and it's quite often worded in that kind of way. Okay, so show an equation or two equations to show the formation of an electrophile involved in the nitration of benzene. Okay, right, I'll use my paper here, I'll not waste it. So here is my benzene, looking all stable and everything. My NO2 plus my nitronium ion. I'm going to use a different colour for my curly arrows. Right, so my electrons, they need to move somewhere. So where are they from? Well, they are in the ring over here. They're going to move to the nitrogen of my nitronium ion. Stage 1. You've done that, you've got a mark. Well done. I now have joined on I've got a bond there. I've now formed a new bond here. So that's my new bond in red. And I have my electron ring. So being careful where I am drawing my remaining ring. I'm just going to show it as a solid horseshoe this time. You could show it dotted if you want. I'm not going to go past that one. I'm going to show it all the way around to there. Okay, so I'm not going past this carbon here. So it's definitely nothing to do with these ones over here. I'm probably even got a bit far on that one, to be perfectly honest. It's looking a bit dodgy now I'm looking at it. Fingers crossed the examiner doesn't notice that one. And I need a positive charge. I had a positive charge over here, so I need a positive charge over on this one. So I'm going to show that positive charge well tucked in there. So I've shown my hydrogen because this is going to be involved in my mechanism, so I'm allowed to show that one. I'm not showing any of the others because it's a skeletal formula. Next stage, so if you get this right and they don't complain about how far you've gone over this one, that's another mark getting your structure and the positive charge. Now I'm going to reform my delocalized ring, so my electrons are going to move from the bond there into the ring. Not going to the carbon, they're going into the ring. Then I've made my product. Can we remember how to name this? Benzene is the important bit on this case, so it's nitrobenzene. What else have I formed? Well, I've formed this H+. So I've formed my hydrogen ion. And oh look, I actually remembered my hydrogen ion here can reform with my hydrogen sulfate ion that I've got over there to reform my sulfuric acid, my H2SO4. So that has acted as a catalyst. It has allowed the reaction to occur and it has not been consumed by itself. Okay, happy days. That's nitration. Before I move on to the next mechanism, I'm just going to I'm going to look at what could happen. So we could make my nitrobenzene. So here's my nitrobenzene I've got. I could do the same again. I could react on another nitronium ion. Now, nitronium ions are still electrophiles, okay? But what happens is this group that's already attached actually withdraws electron density from the benzene ring. So it actually makes the benzene ring kind of less attractive to the electrophiles. Now it will work, so this first step would probably happen pretty easily, pretty exothermically. By the time we get into this point, we might have to do a bit of effort to make the reaction occur. And the more you put on, the harder it will get to get the next one on. But we'll do it, and here we go. So let's try it again. So the electrons are going to go from the ring to the nitrogen. I then move on to step 2. Now there are rules about where you're likely to attach them onto, and we don't need to know them. It's got to attach onto there, and I'm going to have my hydrogen sticking on there as well. So this time, my ring, I'm going to be even more careful this time. Definitely not past those. My positive charge I'm going to show there. So this carbon's got 4 bonds only. My delocalization has been broken. The positive charge is in the ring, and I'm going to reform it by sending those electrons back in. So I've got my nitro down here, my nitro over here, and I've got a full ring. So this is going to be number 1, number 2, number 3. So 1, 3, dinitro benzene. There, done. Pause while I have another sip of my caramel latte. Okay, so uses of these nitrated benzenes. I'm going to really focus on one. We will look at case later where we take this nitro group and we do subsequent reactants on to make an amine with it. But for now, I'm just going to look at these. So this molecule here, so we've got 1, 2, 3, 3 nitro groups, and we've got a methyl group. So this would be 1 methyl, 2, 4, nope, 2, 1, 2, 3, 4, yes, 5, 6, trinitro benzene. I had to work hard at that because it's the first time I've ever named it like that, because I always call it TNT. Trinitrotoluene. So toluene, for info, is that. Okay, it's a relatively common solvent. Methyl benzene. It's just the old days we called it toluene, and I still do, and that's where the name came from. So trinitrotoluene. So you might be familiar with that as an explosive. So this stuff, it blows up, used for mining and all kinds of stuff, sort of sticks of dynamite or something maybe, I don't know. Anyway, this stuff's a solid, and it will react quite readily with oxygen in a very exothermic reaction. Okay, so its delta H is very negative. It produces a lot of energy out of this. And the other thing that it produces a lot of is gas. Oops. So all these species would exist as a gas in terms of our reaction. So I'm producing from 10.5 moles of oxygen here. I'm going to make, what's that, 1722 moles of gas over on this side. So you're producing a lot of gas very, very quickly. That's why it explodes. It blows out as well as producing a lot of heat energy. So a lot of explosives work by creating a lot of gas in a very, very short time. And that's how this stuff works. So yeah, that's these. That's nitration done. So I'm going to move on to the next one now. So this one is Friedel Crafts Acylation or Acylation. So this is a way that we can get our carbonyl chemistry into our benzene chemistry, because everyone loves a good carbonyl. Right, so this one is another one where you've got to know how we make our electrophile. So we're going to start off acylation. If you remember, we've got we like to use acid chlorides quite often. Okay, so if you don't remember, we've got a carbonyl attached to a chlorine. This is quite a good leaving group. The carbon's going to be very delta positive, blah blah blah, all that kind of nonsense. What we're reacting at this time is aluminium trichloride. Now this is a funny species. Aluminium we think is a metal, but it does have quite a lot of covalent character about it, and it can pick up the chlorine from this. So what happens is these two things will react. This becomes positive, so this is going to be our electrophile, and we've got our aluminium, this time tetrachlorate, I guess. No, it's not chlorate, I don't even know what it is. The negative ion on it anyway. So this is going to be our electrophile, and we will try and remember to show this as a catalyst again, because it won't be used up, it will be reformed by the end. Fingers crossed anyway. Right, so we've got an electrophile, we need a benzene. So here's my benzene. Here's my electrophile, so my R just represents something else. I could have done a methyl group, but just not. Right, make sure all my corners come together. Watch out for that, it's so easy to do when you're getting lazy. Right, first movement. My electrons are moving, remember, not this, these. So the electrons are moving from the ring to the positive part of the electrophile. So remember, that's the carbon. So then, hopefully, tick, got a mark. Doesn't really matter where you show these attached to, just as long as it's right. So there's my C, there's my O on my carbonyl, and I've got an R attached. What else have I got attached to this carbon? Well, I've got the hydrogen that's still there that we're not shown. Now we need to show what's happened to our ring. So I might go dotty for a change this time. So now I've got a broken, delocalized ring, and I've got a positive charge in there as well. So that positive charge that was on the electrophile is now delocalized in the ring, or stabilized within the ring, and tick, get a mark for this structure here. Next step, we're going to break this bond. So the electrons from that bond are going to return to the ring, so they're going to pop into there. So now we have made our acylated product. That's an O, my R's here, and I've got an H plus that's been released. So got to show this being reformed as a catalyst, so my H over here, HCl, aluminium trichloride. There we go. Done. Yeah, Friedel Crafts Acylation. Might go through this again with a with something sat on. Okay, let's just look at an example. I'm going to go for a crazy one. I don't even know if this thing will exist. Right. Here's my benzene. I'm going to have benzoyl chloride. So I want to react these two species here, and I'm going to make something exciting. So what do I need? I need my first part. I need to make my electrophile. So I'm going to take my acyl chloride. I'm going to react it with aluminium trichloride. This is going to produce my electrophile here, and my aluminium tetrachloride with a negative charge that I can't remember what I'm supposed to call it. Now I take my benzene, Step 2, my mechanism. There's my benzene. I'm going to change my rotation a little bit here. That's got a positive charge. Get my red pen out. Drop that with there. This is going to come in here. We're going to form a new bond. So I have one benzene ring. I have a carbonyl attached to another benzene ring. This benzene ring is intact. This benzene ring, however, is no longer intact. There we go. I've got a positive charge in there as well. Don't forget, I've got my hydrogen. I'll show them coming this way. Okay, so that's my intermediate structure. We've got to show loss of the hydrogen now, so that's going to come in there. So both electrons from that shared pair of electrons there popping into the ring. And this is my molecule that I have made here. And isn't it pretty? And don't forget my hydrogen. It just looks so nice and symmetrical, that. Isn't chemistry wonderful? Right, anyway, so we've looked at some mechanisms. So we've looked at nitration, where we take concentrated nitric acid and concentrated sulfuric acid to produce a nitronium ion. Excuse me. That nitronium ion is then our electrophile, which would make a nitrated benzene. And we've looked at a Friedel Crafts Acylation reaction, where we use a Friedel Crafts reagent, our aluminium trichloride, and an acid chloride to produce our electrophile. Then we do our reaction, and then we've made an acylated benzene. So these are then useful for doing other reactions with. I can't remember what else I've done in this video, so yep, hope you enjoyed it. Any questions, please do give me a shout, and I will see you later. Goodbye.